Hi, good afternoon, everyone. Thank you all for tuning in to this presentation. My name is Bunyu, and I recently graduated from the MTech Intelligence Systems program in July, and I'm currently working as an analyst in SingHealth. So today, I'll be sharing on my project titled The Intelligent Hand-Based Rehabilitation System for Stroke Patients. These are the topics that I'll be going through with you today. First, I will give you an overview of the problem background, as well as some related work and materials. Then I will move on to the 3D hand joint triangulation tool, as well as the Convolutional Bidirectional LSTM model that we have developed for this project. So first of all, I'll give you an overview of the problem background, as well as an introduction to the project. So for this project, the problem belongs to the field of pose estimation. So here, pose estimation refers to the task of estimating joint positions or key points from an input, such as an image or a video of a person. It is used in a variety of tasks, such as human activity recognition, movement tracking, and assessment. So the main challenge with this task is in estimating the joint positions due to ambiguity and self-occlusion of the joints by other body parts. At this point, some of the current methods that have been proposed to solve this challenge include kinematic skeleton models, as well as deep learning-based models. In particular, one of the more well-known models is the OpenPose model, as you can see from the bottom over here. For this project in particular, the main challenge is that the current process of measuring the angles or range of motion of the hand digits is extremely time-consuming and tedious. Hence, there is a need to develop an automated solution to save time and reduce the manual effort required for this task, which is in the form of an intelligent hand pose and joint tracking system to measure these joint angles automatically. For this problem, there are also some key challenges and issues that need to be addressed. So firstly, as depth images are required for estimating these joint positions, we first need to set up the depth cameras and then determine the parameters for this setup, such as the hand area region, as well as the intrinsic and extrinsic parameters for the camera setup. Secondly, since deep learning models usually require a large dataset to train an effective model, there is a need for a solution to collect and annotate these images. As we are dealing with 3D joint positions, these coordinates can also be very hard to annotate, since there is also the need to estimate the depth or the z-axis coordinate given a 2D image such as this. For this task, manually annotating these joints is also very time-consuming and very prone to error. So there is actually a need for an automated solution to collect and annotate these joints as well. Last but not least, the open source datasets that are currently available are often position and view specific and may not generalize well for another environment. In addition, the single view images are also very prone to ambiguity and self-occlusion in certain positions, as you can see here. Now I'll also briefly go through some of the existing work and materials that have been proposed for this challenge. So the purpose of this review is to actually determine the state of the art of such hand pose estimation models and to explore possible pre-processing steps and methods for our use case. Based on the current landscape, the top models are usually deep learning-based models and have been trained on depth maps alone. Most of these methods use different pre-processing methods, such as voxelization, point clouds, and truncated signal distance functions, TSDF, in order to extract more features from these depth maps. Kinematic hand-based models have also been explored, which basically use the hand structure as a constraint to guide the estimation model. However, some of these methods also suffer from long processing times, inability to deal with occlusions, and also limited generalizability to different viewpoints of the hand. In terms of open source datasets, most of them are fairly large in size, but are also limited in terms of the viewpoints and hand poses, as you can see from the table below. We also noted that the trained models perform well on testing sets, but also lack the ability to generalize in a real-time environment. So for the existing models that have been proposed, most of them have also provided their code as open source repositories, which were also useful when developing the data pipelines for use case. As for the model performance, they also vary across different benchmark datasets. For example, the V2V postnets actually performs well on the ICVL and NYU dataset, but not as well as the dense regression for the MSRA dataset. So now I'll be going through the development of the 3D hand-joint triangulation tool, which was developed to collect and automatically annotate joint positions for a multi-view dataset as shared earlier in the presentation. As mentioned earlier, the open source datasets that are currently available are often position and view specific and might not generalize well to other environmental setups. At the same time, manually annotating these datasets is also very difficult and time-consuming. So there is a need for a semi-automatic or automated method for generating and labeling these sort of datasets. Some of the current methods include attaching sensors to track and then map the hand-joint positions together with the collected images, such as using the lead motion controller, as well as custom semi-automated tools that estimate the annotations based on a few manually annotated keyframes. One of the more promising methods, however, is the Multiview 3D Reconstruction method, which is a proposed method that has been used by OpenPose and Freehand to generate their own datasets. And this was selected as the method for use case as it was able to annotate the positions fairly quickly and accurately. For this method, it uses 2D key points for multiple viewpoints in order to triangulate the final 3D key points. So some of the advantages of this method are that it's able to provide information on occluded positions and also to reinforce poorly detected joints in order to provide an accurate 3D annotation set. In addition, it also requires only RGB images, which can be obtained using multiple low-cost web cameras, for example. However, this method also requires calibration of the cameras, such as the extrinsic parameters, which actually represents the relative camera locations to each other, like this one shown over here. You also need to be able to have multiple camera setup, as well as GPUs to process the images fast enough. As you can see here, this is an example of how the cameras can be set up. Like this one over here, there are two cameras where one is on top and one's at the bottom, but they're both facing the same object. So this is the overall pipeline for the multi-view triangulation method. First, the RGB images are collected from the stream using multiple cameras, which are then used to obtain the projection matrices and calibrate the cameras. Next, the hand image is cropped up by detecting it based on a certain depth or a distance threshold and passed to the detector. Or it can also be detected using the OpenPose detector that comes along with it. For each of these images, the 2D hand joint positions are then detected, shown over here, using the OpenPose model. After that, this 2D coordinates are also filtered by their confidence scores, which range between 0 to 1, where 1 is actually the most confident score, according to a set threshold such as 0.2, and then they are triangulated using the singular value decomposition method, or SVD, in order to obtain the final key points and save for use data. Now I'd also like to show you a short demo of how the tool works. As you can see here, the 2D key points are being detected on the RGB images, and the reprojected points after the triangulation is shown on the depth images below. So the performance of the tool actually depends on the number of cameras that you use And naturally, the more cameras that you use, the better the estimation of the final 3D hand joints. One of the benefits of this tool is that it can also be deployed real time, and it can also be used for the task of estimating the hand joint positions if there are multiple cameras available. So now that you have seen the triangulation tool that has been developed, I will now share on the convolutional bidirectional LSTM model that has been developed for our use case. Now, earlier on, I shared on how the 3D hand joint triangulation tool can be used to collect and annotate hand image datasets, and also how it can be used to estimate the joint positions in the real-time setting. However, this tool also requires multiple camera setup, which might not be readily available in every setting. So the objective of this model is to predict the joint positions using depth and/or RGB images from a minimal number of cameras, such as a single camera source. So basically for this model, it takes in a sequence of spatial inputs, such as 2D depth images, and extracts the spatial features from each image using a CNN, a common CNN block. As you can see over here, the images are first centered and cropped, and then passed on to the common convolutional block for spatial feature extraction. These features are then flattened and then passed to the LSTM layer in order to extract the temporal based features, meaning across the sequence itself. So for this method, it has been successfully used in other applications, such as classifying video sequences and image slices, such as MRI scans. One of the advantages of this approach is that it is able to make use of past hand positions in order to refine the current estimates. In a way, it is like simulating a multi-view approach, but only using a single image source. So for this model, it was trained using the MSRA, ICVL, and NYU datasets for 10 epochs each, and were tested using the testing sets that came available with each dataset. However, based on the benchmark metrics, the model did not seem to perform as well as some of the state-of-the-art models. When this was examined further, we found that the LSTM layer seems to be able to learn and make use of the past few hand images in order to extract the current position estimates. But the CNN layer might not have been sufficient for extracting the spatial features for further use by the LSTM, that means on the hand shape itself. And this can actually be improved by more sophisticated convolutional trunks such as ResNet or BGG16. At the same time, we also did a visual inspection of the sample predicted joint positions on the depth image and plotted them out as shown over here. And it shows that it actually performs well for certain positions. For example, the open palm and some hand positions with a certain degree of flexing, they perform well. But in other challenging positions, such as this one, for example, did not perform as well. One other interesting thing to note is that the model is also sensitive to the range of depth values. So the calibration step in the beginning, when you perform the image pre-processing, it will be important to do it for the model to perform effectively. Also, this model was tested in a real-time deployment setting, and it showed that it was able to capture the relative structure of the hand correctly, but not as well for predicting the exact positions of the hand shape, as you can see here. And as mentioned earlier, it's also heavily reliant on pre-processing steps such as cropping and centering to perform effectively. So this is a demo of the model that was trained on the ICVL dataset. As you can see, it tracks the hand structure quite well, and it's able to track them across the frames using possibly the LSTM layer. But in terms of the exact hand positions, it might not estimate them very accurately. As you can see, it's actually tracking the movement of the hand quite well. Now, I've come to the end of the presentation. So I'd like to close it off by giving you a summary, as well as some learning points from this project. So for this project, a 3D triangulation tool for automated collection of hand images and annotated 3D joint levels was developed. And it can also be used as a baseline method for estimating these joint angles. Although the convolutional bi-LSTM model didn't perform as well, it shows promise for further development with a better spatial feature extractors. In short, some future work will include experiments on the custom dataset collected, as well as better methods to improve the spatial performance of the model. So to cap it off, here are some learning points that I've gained through this experience. Through this project, I've gained very valuable experience in working with actual cameras, as well as 3D image datasets, which has also provided me an opportunity to apply the skills that I have learned throughout the course. I've also had the opportunity to develop complete data pipelines from the data source right up to deployment, which was also very challenging and very useful. Last but not least, I'd also like to thank NUS ISS and the MTech IS lecturers for the opportunities and skills that they have taught throughout the course, as they were very helpful throughout towards the work done in this project. So with that, I have come to the end of my presentation, and I hope you have enjoyed this and learned something from it today. Thank you for your attention, and have a nice day.